A Bayesian analysis of AFL team patronages using Mikey touch-on and touch-off data. By Shane Smith, Parikshit Sreedhar, and Matthew Bolton. Matt, Parry and Shane have purchased an AFL merchandise store near Sandringham Station. The owners seek to maximise merchandise for the popular teams in the area while carrying less stock for teams with fewer supporters. Data was sourced from the Melbourne Datathon, comprising of 1.8 billion transactions. Data pre-processing was undertaken to consider only ticket transactions at relevant times on game days versus non-game days, at railway stations near Melbourne's football stadiums. Trips were filtered to only include commuters arriving at these stadium stations in a relevant time period before the match, or departing a stadium station after a match. This data was further filtered to provide a tally of Sandringham football commuters. A similar approach, with similar time intervals, was taken for non-game days to provide a baseline number of commuters. Count data often follows the Poisson distribution. The Poisson distribution is defined by a single parameter lambda that gives both the expected value and the variance, as these are both equal. Linear regression cannot be used for data taken from this distribution, as it assumes that the variance is homoscedastic, or unchanging, whereas variance increases as the expected value increases in the Poisson distributed data. Log linear regression takes the form lambda equals e to the beta naught plus beta 1 x1 plus beta 2 x2, etc. Or alternatively, the log of lambda equals beta naught plus beta 1 x1 plus beta 2 x2, and so on, hence why it is referred to as a log linear model. It would be nonsensical to have negative number of commuters. E raised to any power cannot be negative, ensuring that there are no negative numbers estimated in the count data. Each variable x is a binary dummy variable, indicating whether the team has played. The estimated value of lambda is the estimated number of commuters depending on which teams are playing. The intercept term reflects non-game day commuters, while the other beta coefficients represent commuters when those teams play, although this is not a direct linear relationship. Although not linearly interpretable, teams with higher beta coefficients have higher levels of support than teams with lower beta coefficients. Matt, Parry and Shane have differing opinions of local team popularity. Their viewpoints will be modelled using 5 different models. These models will differ in their estimated values of the beta coefficients and degree of belief in those prior estimates. Matt's expert knowledge accurately reflects the data. Shane is confused and suggests expert knowledge that differs substantially from the data. Matt and Shane's priors will be modelled twice, reflecting differing degrees of belief. These prior estimates were taken from classical estimates of Sandringham and another station that differs greatly. Perry does not have a view either way and will model using non-informed priors. As we know that Matt's priors reflect the data, this will effectively be an unchanging benchmark. We aim to see the effect of non-informative and wrong priors on the posterior distributions. The model diagram is set out horizontally to save space. Yi is distributed according to the Poisson distribution with the parameter lambda. Lambda is given by the log linear regression equation, with each beta coefficient distributed normally. The model diagram was then coded for JAGs. Note that the dispersion of the normal distribution is given as precision. The values of the priors are not shown here, as 5 models were run. These values will be summarized and presented in tables instead. As previously stated, correct, incorrect, and non-informative priors were tested. Although the differences in the beta coefficients varied by team, some teams were markedly different in the priors assumed by Matt and Shane. The largest of these differences was in support for Essendon, although St Kilda was also quite different. The coefficients of the correct models are not expected to change greatly as they already reflect the data. The non-informative prior is expected to converge on the beta coefficients given by the correct model. The incorrect model may dominate the evidence, but should be starting to move towards the correct model. The weak incorrect model should converge more so than the strong wrong model. With 18 variables plus an intercept across 5 models, there were 95 diagnostic plots generated, too many to analyse in this presentation. However, the 2 selected here are representative of the different models and coefficients. Looking at the time series plot in the upper left, both coefficients demonstrate chains that are well mixed and therefore representative. Also indicating representativeness, the shrink factor in the bottom left is less than 1.1 and falling, although for beta 15, this decline is after an initial rise. In the top right plot, autocorrelations are low, with only a few significant lags. Consequently, the effective sample size is over 10,000. These both indicate accuracy of the model. The estimate of the parameter value shows that all chains agree, and there is a low Monte Carlo standard error. This also indicates model accuracy. The next 4 slides compare parameter estimates of the coefficients for the 2 strong models. The correct strong model is on the left, and the strong wrong model is on the right. Although the highest density intervals of both models overlap for most of these teams, the estimates for Essendon do not overlap. The models disagree on this point. For the next 6 teams, the models are in agreement, with an overlap in the HDI. Of particular note are Geelong, Hawthorn, and Melbourne. For the next 6 teams, the models agree generally with overlapping HDIs. Richmond is pretty close, although St Kilda only just overlaps. The models disagree, however, over the Western Bulldogs. The 95% HDIs do not overlap. As to be expected, the R-squared of the model with the correct priors is higher than the R-squared for the strong wrong model. Classical statistics cannot produce a distribution for R-squared. However, these 95% HDIs do not overlap. The estimated coefficients for the 5 models can be compared. Models 1, 2, 3, and 5 have all converged on similar estimates of the beta coefficients. Only the strong wrong model disagrees. Even the weak wrong model has been drawn in by the weight of the evidence. Turning to the percentage differences, the strong wrong model is particularly contrasting, performing very differently to the other models. This suggests that with broad variance or many observations, Bayesian analysis performs robustly, even with incorrect priors. The 3 teams with the highest coefficients are Richmond, Melbourne, and St Kilda, suggesting that locals near Sandringham Station support these 3 teams. Passenger numbers at Sandringham increase markedly when Richmond is playing, followed by Melbourne and St Kilda. Parry, Matt, and Shane should stock more merchandise of these 3 clubs.